A million miles from home, in the quiet equilibrium of deep space, a golden mirror unfolds like a metallic flower. The James Webb Space Telescope floats beyond the pull of our planet, suspended in the stillness at Lagrange Point 2, where sunlight and gravity balance with delicate precision. From this vantage, it looks outward, past the planets of our solar system, past the scattered dust of ancient stars, into the unbroken dark. Webb does not see light as we do. It feels it. It captures heat, the infrared shimmer of distant worlds, the warmth of suns that have long since faded from human memory. Each photon it catches has traveled across centuries of emptiness, bringing a fragment of a story written by time itself. Among those fragments, scientists have found something extraordinary. Light from a planet 124 light-years away carries chemical signatures that do not fit neatly into the patterns of geology or weather. The spectrum shows hints, subtle, tentative, of gases that, on Earth, are known to be shaped by life. Not proof, not yet, but a whisper that refuses to be ignored. Webb's instruments have done what no telescope before it could: read the invisible breath of another world. To understand what that means, we must step back. Light, after all, is a messenger. It travels at a constant speed, untouched by time, revealing the composition of atmospheres through delicate color shifts. By splitting this light, scientists can tell what molecules float above distant worlds. Water vapor, carbon dioxide, methane, each absorbs light in a unique way, leaving its fingerprint behind. These patterns, called spectra, are our best chance of finding life beyond Earth without ever leaving home. But this discovery, this spectral anomaly, goes beyond the routine detection of gases. Its arrangement, its ratios, its faint imbalances between methane and carbon dioxide suggest something more dynamic, something that might be sustained by active processes. It could be geological, yes, volcanic reactions, photochemical cycles, or exotic chemistry can mimic biological patterns. Yet the possibility that this balance exists because something there breathes has ignited cautious excitement. The James Webb Telescope has changed our relationship with the unknown. Where once our ancestors looked at the stars and saw gods, now we see chemistry, physics, and perhaps life. In the next chapters, we'll explore what truly defines a biosignature, why this signal stands apart, and how the telescope's sensitivity is reshaping our understanding of habitability itself. Before we can decide whether that spectral whisper truly hints at life, we must understand what scientists mean by a biosignature. The term sounds simple, a sign of life. Yet in practice, it is one of the most complex ideas in modern science. A biosignature is any measurable feature that could not easily exist without the influence of biology. On Earth, that might be oxygen in the air, methane from microbes, or pigments that absorb sunlight for photosynthesis. But in the cosmos, the meaning becomes slippery. Planets are unpredictable laboratories. Volcanoes can mimic biology. Radiation can fracture molecules and rearrange them into confusing forms. So when astronomers look at light from distant worlds, they must separate what looks alive from what merely acts alive. To do this, scientists rely on spectral fingerprints, the way each molecule absorbs and emits light. When starlight passes through a planet's atmosphere during transit, gases there leave behind tiny gaps in the spectrum, like missing notes in a song. Those gaps tell us what the atmosphere contains: water vapor, carbon dioxide, methane, all familiar patterns. But no single gas is enough to prove life. The key lies in combinations. On Earth, for instance, oxygen and methane cannot coexist for long. They react and destroy each other. Their continuous presence means something must constantly replenish them. In our case, living organisms. That is the logic astronomers apply beyond our planet. A true biosignature, then, is not just the detection of one exotic molecule, it is the discovery of disequilibrium, a set of chemicals that should not persist together unless something active, possibly biological, is maintaining them. Yet even that is not proof. Abiotic processes, such as ultraviolet radiation, breaking apart water, or carbon reactions on hot rock, can mimic biological outputs. That is why each potential biosignature must be analyzed in the context of the planet's temperature, pressure, stellar radiation, and geological behavior. This is the great paradox of astrobiology. We are searching for life we have never seen, using the only example we know, our own. Earth's biosphere teaches us what gases life can produce, but alien biology might follow entirely different rules. What if life elsewhere breathes methane instead of oxygen, or uses sulfur instead of carbon? What if its chemistry leaves behind no familiar fingerprints at all? These are the questions that keep scientists cautious, even when faced with data as intriguing as the new 124 light-year signal. The Webb telescope has opened a door, but not a verdict. Each spectrum it captures must be interpreted with humility, tested against physics, and compared to Earth's intricate lessons. True biosignatures aren't loud announcements. They are quiet harmonies, hidden in the light, waiting for careful minds to recognize the pattern. Light is the oldest messenger in the universe. Long before there were telescopes, detectors, or even eyes to see, light was already carrying the stories of creation across the void. Every beam that touches us today has traveled through unimaginable distances, filtered through dust, gas, and magnetic fields, recording in its vibrations the fingerprints of the matter it encountered. For astronomers, deciphering those fingerprints is an act of translation. They take the faint shimmer of a faraway star, separate it into colors, and search for subtle dips and rises in brightness. Each tiny variation tells of something real: a molecule absorbing light, an atom releasing energy, a planet blocking part of its sun. The James Webb Space Telescope was built to master this art of reading invisible patterns, particularly in the infrared, where the glow of life's chemistry often hides. Infrared light is heat, the silent language of molecules in motion. When a planet passes in front of its star, a portion of that starlight filters through its atmosphere. Molecules within that air absorb specific wavelengths, creating a pattern like a barcode. To the untrained eye, it looks like noise. To scientists, it's a complete conversation. Water vapor leaves one signature, carbon dioxide another, methane a third. Together, these form an atmospheric identity card, the first clue to what kind of world we're observing. JWST's instruments, particularly IR-SPEC and MIRI, are sensitive enough to detect these faint modulations, even when the planet itself remains unseen. But the anatomy of alien light is never simple. Stellar activity, flares, magnetic turbulence, or the star's own chemical makeup can distort readings. Cosmic dust can scatter photons, making molecules appear where none exist. That's why astronomers record multiple transits, stacking data again and again until patterns repeat. Only then do they begin the painstaking task of modeling the atmosphere, temperature layers, cloud thickness, molecular ratios. Each curve in the data becomes a clue to the planet's environment, whether it's steamy, frozen, stormy, or calm. In the case of the planet 124 light-years away, Webb's instruments caught something that defied easy categorization. The spectrum suggested the presence of methane and carbon dioxide in unusual proportions, a chemical tension that on Earth rarely persists without biological help. Yet, it could also arise from a geothermal activity or unseen chemical cycles unique to that world. The challenge lies in distinguishing between life and the illusion of life. To truly understand the anatomy of alien light, scientists must combine physics, chemistry, and an artist's patience. Each spectral line is like a brush stroke on a vast, invisible canvas. Fragments of color that, when aligned, reveal the portrait of a distant world. Webb has given humanity eyes that see heat, patience that measures centuries, and questions that stretch even further than its mirrors. Light has always been there, but only now are we learning to listen to its language completely. Every planet that circles a distant star exhales, not in the way a living creature does, but through the slow, constant exchange of gases between surface and sky. Volcanoes vent minerals, oceans evaporate, rocks release and absorb carbon. The balance of these gases shapes a planet's climate and, in rare cases, reveals whether something more than chemistry is at work. The James Webb Space Telescope, with its golden eye for heat and motion, was designed to read this invisible breath. Its mission is not simply to see worlds, but to taste their air, to decode the stories their atmospheres tell. When a planet crosses its star, a portion of that starlight filters through its atmosphere before reaching us. In those few hours, JWST becomes a cosmic prism, splitting light into thousands of wavelengths and recording how much brightness is lost at each one. Certain molecules absorb specific wavelengths: water, carbon dioxide, methane, ammonia. Each leaves a distinctive imprint. By comparing light before, during, and after the transit, Webb reconstructs the planet's atmospheric recipe. It's like smelling an aroma carried on a breeze, and knowing whether it came from the sea, the forest, or a fire. Yet the process is far from simple. The differences JWST measures are astonishingly faint, sometimes less than 1/100% in brightness. Even the smallest disturbance, such as a fluctuation in the star's output or a cosmic ray striking a detector, can distort the signal. That's why the telescope's instruments must remain cryogenically cold and shielded from sunlight, so they can detect the planet's subtle warmth without interference. Its detectors, NIRSPEC for near-infrared light, MIRI for mid-infrared, operate like twin senses, one tuned for the whisper of water and carbon, the other for the heavier tones of organic molecules. After the data is collected, scientists on Earth perform an intricate dance of subtraction. They remove the influence of the star, filter noise from cosmic dust, and run simulations of potential atmospheres until the model that fits emerges. What remains is the spectrum, the chemical fingerprint of the planet's breath. But interpreting it requires more than pattern recognition. It requires judgment, context, and restraint. Methane might hint at biology, but it can also arise from geological heat. Oxygen might suggest life, but it can be forged by ultraviolet light, tearing apart water molecules. To claim a biosignature, scientists must see not just one molecule, but a harmony of interactions, gases in chemical tension that should not coexist unless something replenishes them. In essence, Webb transforms light into a kind of truth serum for worlds. Every spectral dip is a confession, every ratio a clue to planetary behavior. Some exoplanets exhale sterile chemistry, others breathe patterns we struggle to explain, and somewhere among them, perhaps already recorded on Webb's instruments, lies the first unmistakable breath of alien life. Quiet, precise, and waiting to be understood. Its name is K2-18b, an unassuming label for what might be the most important planet yet observed beyond our solar system, located 124 light-years away in the constellation Leo. This world orbits a cool red dwarf star that glows just faintly enough for its planet's atmosphere to be seen in contrast. What makes K2-18b remarkable is not only its position within the star's habitable zone, but the whispers coming from its skies, a delicate mix of gases that could redefine our understanding of where life can exist. K2-18b is what astronomers call a Haitian world, a hybrid of hydrogen and ocean. It is larger than Earth, about 8.5 times our planet's mass, yet smaller than Neptune. That size once seemed too big to host life as we know it, but recent models suggest such planets could sustain deep oceans beneath thick, hydrogen-rich atmospheres, creating warm, pressurized conditions that protect liquid water, the essential ingredient for biology. Unlike the frozen, airless moons of our solar system, or the scorched deserts of close-orbiting exoplanets, a Haitian world offers a middle ground, neither too harsh nor too gentle, but balanced on the knife's edge, where chemistry becomes something more. When the James Webb Space Telescope turned its instruments toward K2-18b, it found signs of water vapor high in the atmosphere, a revelation that electrified the scientific community. Even more intriguing was a faint but persistent signal at specific infrared wavelengths, possibly indicating the presence of dimethyl sulfide, a molecule on Earth produced almost exclusively by marine life. Though far from proof, its detection forced astronomers to confront a thrilling possibility that we may have glimpsed a biosignature, a chemical trace of living metabolism on a world light years away. The planet's environment is, of course, alien. Its year lasts only 33 Earth days, and its skies glow dimly crimson under a shrunken sun. Temperatures could hover near the limit where water remains liquid, perhaps under an endless blanket of the mist. If oceans truly exist, they might stretch for thousands of kilometers, shrouded in perpetual twilight. Any potential organisms would live beneath high pressure and filtered starlight, evolving under conditions we can only imagine. Yet the chemistry of life, the interplay of carbon, hydrogen, oxygen, and sulfur, might still find a foothold there, proving that biology can adapt not just across continents, but across cosmic scales. Scientists remain cautious. A false positive could arise from volcanic activity, from lightning chemistry, or even from instrumental noise. That's why Webb's findings are being tested and retested with every available model. But even with uncertainty, the implications are profound. For the first time, a telescope has not merely seen a distant world. It has sniffed it, sensed its air, and found something eerily familiar within it. If confirmed, K2 to 18b could become the first world outside our solar system, where the line between chemistry and life begins to blur. And for humanity, it would mean that the story of biology is not Earth's alone. It is a universal narrative written across the stars. What if it's not noise? What if, for the first time in human history, we've truly seen the breath of another biosphere? Imagine a world where clouds carry the scent of oceans that never knew Earth's tides, where invisible winds stir molecules born not of volcanoes or storms, but of life. The faint signal JWST caught from K218b is just a whisper in the cosmic static. But if that whisper is genuine, it could change everything we believe about existence itself. For centuries, we've gazed at the stars and wondered if someone or something was looking back. Now, for the first time, the question isn't if life could exist elsewhere, but where it already does. A simple chemical trace, one invisible pattern among billions, could be our first glimpse of a second Genesis. Not bacteria from Mars, not fossils and meteorites, but a living world orbiting a distant sun, sending a signal through physics, light, and time itself. The idea seems impossible. A molecule like dimethyl sulfide could have traveled 124 light years, passing through cosmic dust, distortion, and starlight, only to be captured by a mirror the size of a tennis court. Yet every discovery in science begins with something faint, fragile, and unbelievable. Electricity, relativity, DNA, all started as whispers against the roar of uncertainty. If this signal holds, it will not just redefine astronomy, it will redefine us. Because this time, the discovery wouldn't be a photograph or a mineral sample. It would be a breath, a proof that life isn't a miracle locked to one pale blue dot, but a pattern written into the laws of chemistry and energy. It would tell us that wherever there is warmth, carbon, and time, nature wants to create. Life is not the exception, it's the expectation. And then, of course, comes the hardest question of all. If the universe gives birth to life so easily, why haven't we heard from it? Are civilizations rare, or do they rise and fall long before they can reach out across the void? Could K218b be teeming with microbial oceans, unaware that far away, another planet just detected their breath? If this signal is real, humanity's loneliness ends, not with a message or a monument, but with a molecule, one spectral line carrying a truth older than language. We are not alone. Every discovery that brushes the edge of the unknown ignites two fires, one of wonder and one of doubt. In the case of K218b, both burn fiercely. Scientists who spent their lives dreaming of alien life now find themselves wrestling with the burden of proof. For if they claim too much too soon, the world will call it fantasy. But if they hesitate, they risk letting history slip quietly through their fingers. The James Webb Space Telescope has handed humanity a riddle wrapped in data, and every scientist who touches it must decide how much belief to let in. The first camp is cautious, almost reverent. To them, the detection of dimethyl sulfide, if real, is a tantalizing anomaly, but not yet evidence of life. They remind us that the universe is a trickster. Methane can form in hydrothermal vents. Oxygen can appear without biology. Spectra can mislead even the most careful observer. They recall how, decades ago, scientists misread Martian canals as artificial structures, or mistook strange chemical reactions on Venus as signs of microbes. For the skeptics, excitement is a dangerous lens, one that can blur the fine line between discovery and desire. Their mantra is simple: extraordinary claims require extraordinary evidence. Then there is the other camp, the hopeful ones, the dreamers cloaked in data. They argue that if we refuse to follow every curious signal, we may never find what we seek. For them, Webb's readings are not proof, but possibility, a reason to keep looking deeper. They see the faint molecular signature as a door half open, inviting humanity to imagine again. If not this planet, they ask, then which one? And if not now, then when? For them, the pursuit of life beyond Earth is not just science, it is destiny. Between these two sides lies the pulse of progress. Science is built on the tension between belief and skepticism, each correcting and refining the other. Hope drives us to explore, and doubt ensures we don't get lost in illusion. Even now, teams around the world are running simulations, comparing K2-18b's atmospheric model against known chemical processes, checking whether the signal could arise from volcanism or lightning instead of biology. Each test could either strengthen the case or dissolve it into noise. Yet, paradoxically, both outcomes push us forward. Even a false alarm deepens our understanding of what doesn't indicate life, bringing us closer to knowing what truly does. The debate has spilled beyond laboratories into headlines, classrooms, and public imagination. For once, the question of life beyond Earth isn't confined to science fiction. It's discussed by astronomers, philosophers, and school children alike. Each person projects their own meaning onto the discovery. Some see hope, others humility, and a few fear. Because if life exists elsewhere, it challenges the very story we tell about ourselves, that we are unique, central, chosen. And so, amid the hum of supercomputers and the silence of deep space, the argument continues. Not a fight, but a dance. Skepticism keeps humanity grounded. Hope keeps it reaching for the stars. Somewhere between them lies truth, shimmering faintly, like the spectral line that started it all. The search for life, at its core, is a search for imbalance, a delicate chemical disorder that nature alone rarely sustains. Planets, left to themselves, tend toward equilibrium. Their gases settle into predictable harmony, every molecule finding its quiet place. Life, however, disrupts that peace. It exhales oxygen, consumes carbon, releases methane, and in doing so, leaves fingerprints of chaos. To find a biosignature is to find a planet that refuses to sit still, a world alive in chemistry long before it's seen in light. Astronomers call these clues spectral fingerprints, patterns of absorption that reveal which gases exist in a planet's atmosphere. But interpreting those fingerprints is a challenge worthy of an ancient riddle. Suppose you detect methane. That's interesting, but not enough. Methane can emerge from volcanoes or the breakdown of minerals deep underground. Add oxygen, and things get intriguing, because methane and oxygen shouldn't coexist for long. They destroy each other. If they both persist, something must be constantly replenishing them. On Earth, that something is life. On another world, it could be too, or it could be chemistry we've never seen. The James Webb Space Telescope pushes this game of deduction into a new era. Its instruments can detect trace amounts of gases, molecules so rare they might represent only a few parts per billion. That precision lets scientists move beyond single molecule detection and toward full chemical ecosystems. The real goal isn't to find one gas, but to find relationships between gases that shouldn't exist together naturally. When the ratios seem impossible, when the chemistry looks unstable yet persists, that's when the whispers of biology begin to emerge. But the universe is a master of mimicry. Geological and photochemical processes can craft false signals, pseudo-biosignatures, that look alive but aren't. For instance, ultraviolet radiation from a nearby star can split water molecules, freeing oxygen into the air. Methane can appear from hydrothermal vents on ocean worlds without a single cell involved. Even dimethyl sulfide, the mysterious molecule seen on K2-18b, could form through high-pressure chemical reactions no human lab has ever replicated. In a sense, each planet is its own laboratory, running millions of uncontrolled experiments simultaneously. Our challenge is to read the results without fooling ourselves. To solve that riddle, scientists combine chemistry, climate modeling, and planetary physics. They build virtual worlds inside supercomputers, simulating every possible source of a molecule, then test whether life is the simplest explanation left standing. Only when all known geochemical and photochemical alternatives are eliminated does the term biosignature begin to hold weight. Even then, humility remains essential. As one astronomer put it, a biosignature is not proof of life. It's an invitation to keep looking. This cautious optimism defines the new scientific frontier, a place where chemistry, physics, and hope converge. Each spectral line is a clue, each molecule a piece of a vast cosmic puzzle. Someday soon, when the right combination of gases appears, balanced in impossible harmony, we may finally know we're reading the signature of something breathing far beyond our sky. There comes a moment in every great discovery when numbers stop being numbers. They begin to breathe, to carry meaning beyond the charts and graphs that birthed them. For K2-18b, that moment arrived when a few subtle dips in infrared light, mere fractions of a percent, became something more than data. They became a story. To the scientists analyzing them, those spectral lines represented a world unseen, yet suddenly real. To the public, they became the echo of a question as old as consciousness itself. Are we alone? It starts in laboratories, with cautious conversations over coffee, with screens glowing in darkened rooms. A single spike on a graph, consistent, repeatable, and hauntingly familiar, pulls researchers deeper. They cross-check calibration data, test against stellar noise, and rerun simulations at 3 in the morning. The excitement builds quietly, like a held breath, and when the signal persists, when it refuses to vanish under scrutiny, something shifts. Data becomes a whisper of truth, and science brushes the edge of belief. Then the story escapes. A preprint appears online. Journalists pick it up. Headlines promise signs of life discovered 124 light years away. Suddenly, what was once confined to data repositories becomes a global pulse. The public reacts with awe and skepticism in equal measure. Social media floods with speculation. Some call it humanity's greatest discovery. Others, another mirage in the desert of expectation. The scientists, meanwhile, retreat further into caution. They know how fragile such findings can be, how easily they crumble when new information arrives. For them, every headline is a double-edged sword, a chance to inspire, but also a risk of misinterpretation. Still, belief spreads faster than data. People want to believe it's in our nature. From the first cave paintings to modern cosmology, humanity has always turned the unknown into narrative. A few molecules detected through a telescope become a mirror for our hopes and fears. Priests see divine creation confirmed. Philosophers see cosmic continuity. Skeptics see a reminder that truth requires patience. Everyone, in their own way, sees themselves reflected in that distant light. In that sense, science becomes something greater than measurement. It becomes myth reborn through mathematics, a myth grounded in evidence, tested by reason, but still reaching for the same transcendent wonder our ancestors felt when they first looked up at the stars. That is the quiet power of belief born from data. It connects humanity across time, turning pixels into poetry. As debates unfold in universities and observatories, one fact remains unchanged. K2-18b still orbits its star, breathing its invisible chemistry into the void. Whether or not life exists there, the data has already done something miraculous. It has reminded us that curiosity itself is a form of life, that to question is to live. The moment data becomes belief, the universe stops being silent. It begins to speak through us. Every search for life beyond Earth is, in truth, a search for ourselves. When we stare into the golden mirrors of the James Webb Space Telescope, we are not merely gazing outward, we are peering into the reflection of human longing. The discovery of possible biosignatures on K2-18b is more than a scientific milestone. It is a mirror held against our collective soul. It forces us to ask what it means to be alive, to belong to a universe vast enough to create countless versions of existence. Some perhaps looking back at us right now. Humanity has always been divided between two instincts: to believe we are unique and to hope we are not. For centuries, philosophers, poets, and astronomers have wrestled with this paradox. Are we the only spark of awareness in an otherwise silent cosmos? Or are we one verse in a grand symphony of life, repeating across galaxies in forms we cannot yet imagine? Every pixel of data from JWST seems to hum with that contradiction. It shows us worlds that feel both familiar and alien, places where physics obeys the same laws, yet the outcomes are wildly different. When scientists talk about K2-18b's possible atmosphere, they speak in units and probabilities, but beyond the jargon lies something deeply human: wonder. It's the same wonder that guided the builders of the pyramids to track the stars, that sent Galileo to his telescope, that made Voyager carry a golden record into the dark. The pursuit of alien life is not just about confirming biology, it's about confirming connection. To find another biosphere is to find kinship beyond blood, proof that the story of life did not end on Earth, but continues, infinite and unfinished. And yet, this mirror also reflects our fears. What if we find life that is unrecognizable, so different that we cannot even call it alive? What if we find nothing at all? Only barren rock and chemical silence? Would that make our existence lonelier or more precious? The cosmos, in its quiet indifference, does not answer. It simply offers light and time, waiting for us to interpret. In doing so, it teaches humility. It reminds us that our species, for all its brilliance, is still at the beginning of understanding what life truly is. Q18b may or may not host organisms. The signal may fade, the data may shift, but something permanent has already changed. Humanity has seen its reflection in a distant world and realized that curiosity is its defining trait. We are a species that builds machines to look for others, and in that act, we reveal the best of ourselves. Even if the stars remain silent, the search unites us. It transforms the coldness of space into a canvas for meaning. So, perhaps the true discovery isn't out there, but within. The realization that our urge to seek life is itself proof of life's most powerful instinct: to reach beyond, to question, to connect, to understand the James Webb Space Telescope's magic. You must first understand its fragility. It is not a machine of brute strength, but of perfect precision, a golden butterfly floating 1,000,000 miles from Earth, unfolding its wings in the cold vacuum of space. Every mirror, sensor, and circuit within it was crafted to sense whispers, not shouts, to detect the faintest traces of heat and light that left their source long before human civilization even began. What makes JWST extraordinary isn't just its size, but its purpose: to turn faint photons into stories about time, matter, and life. At its heart lies a 6.5-meter segmented mirror made of beryllium and coated in a pure gold. Each of its 18 hexagonal panels reflects infrared light, the glow of warmth that stars, dust, and planets emit even in darkness. Unlike visible light, infrared can slip through cosmic clouds and reveal what's hidden, forming galaxies, infant stars, and the dim glow of exoplanets orbiting faraway suns. For biosignature hunting, this sensitivity is everything. Many molecules associated with life, water vapor, methane, carbon dioxide, ozone, speak their chemical language in the infrared spectrum. JWST was designed to listen. Its instruments form a symphony of precision. NIR-SPEC, near-infrared spectrograph, acts like a prism, splitting starlight into countless wavelengths so scientists can read a planet's atmospheric barcode. NIR-CAM captures those faint glimmers through filters fine-tuned to isolate spectral clues. MIRI, mid-infrared instrument, goes deeper, detecting cooler, older emissions, the quiet glow of chemistry that might persist in habitable zones. Together, they make JWST not just a telescope, but a living laboratory orbiting in silence. But precision comes at a cost. The telescope operates at just a few degrees above absolute zero. Its massive sun shield, the size of a tennis court, protecting it from the heat of the sun, earth, and moon. Without that shield, the instruments would drown in their own warmth. Its orbit at the L2 Lagrange point keeps it in perfect balance, far enough from Earth to stay cold, yet close enough to send its data home. Every day, terabytes of information travel across deep space antennas, arriving on Earth as ghostly streams of binary code that scientists translate into images and spectra, the language of light turned into the language of discovery. What's astonishing is how much must go right for every observation to work. A single misalignment of one mirror by a fraction of a millimeter could ruin an entire data set. Engineers devised micro actuators so precise they move mirror segments by distances smaller than the width of a human hair. This mechanical poetry keeps the telescope tuned to perfection, transforming photons that traveled for centuries into evidence of worlds that may host oceans, clouds, or life itself. The James Webb Space Telescope is often described as a machine, but in many ways, it behaves like an organism, sensitive, adaptive, alive to the cosmos. Its heart beats in the pulse of data it sends back, and its vision stretches further than any human eye ever could. Light is the oldest storyteller in the universe. Every star, every planet, every atom emits a tale written in photons, but most of these stories are invisible to the human eye, whispered not in visible colors, but in wavelengths far beyond what we can see. That's where the James Webb Space Telescope listens. It doesn't look at the universe the way we do. It feels it, reading warmth instead of brightness, hearing the echoes of creation in a register of light too deep for our senses. Webb listens in infrared, and in that hidden language, the cosmos reveals its secrets. Infrared light is the color of heat. It streams from stars as they form, from galaxies as they grow, and from planets that glow faintly in reflected warmth. To human vision, these sources are dark, cloaked by dust and distance, but to Webb, they blaze with clarity. Its detectors, cooled to near absolute zero, can catch the faintest exhalation of warmth from a distant world. A planet that's invisible to the Hubble telescope becomes a glowing ember through Webb's eyes, and when that light passes through a planet's atmosphere, molecules like water vapor, methane, and carbon dioxide leave telltale imprints in the spectrum, traces of possible life. Infrared astronomy is more than a new way of seeing. It's a way of time travel. Because the universe is expanding, light from ancient stars stretches as it travels, shifting into longer, redder wavelengths. By the time it reaches us, that light carries the imprint of the early universe itself, the moment when galaxies first awakened. Webb doesn't just peer into space, it peers into history. Every image it captures is a fossil of light billions of years old. For biosignature science, this ability is revolutionary. Many of the molecules that signal biological activity emit or absorb energy primarily in the infrared range. On Earth, we use the same principle in spectroscopy to analyze the composition of our own atmosphere. JWST applies that principle across unimaginable distances. When a planet passes in front of its star, Webb records the slight dimming of starlight and the subtle shifts in wavelength caused by atmospheric absorption. From those patterns, scientists can reconstruct what that air might contain, even if the planet itself is nothing more than a shadow in the data. But the challenge is that the infrared universe is also noisy. Thermal radiation from dust, starlight, and even the telescope itself can interfere. To separate truth from illusion, astronomers run layers of calibration, modeling, and filtering, peeling back cosmic interference. Like archaeologists brushing dust from an artifact, each refined image, each sharpened spectrum is a victory, not of luck, but of patience and precision. Infrared, once invisible to us, is now our most profound connection to the universe's hidden life. Through Webb, we've gained not just new eyes, but new senses. We are no longer blind to the warmth of other worlds, or deaf to the whispers of ancient stars. The universe has always spoken in infrared. We simply learned how to listen. Beneath the shimmering haze of K2-18b's atmosphere may lie something extraordinary, an ocean that never meets the light of its star. Scientists call it the hidden ocean hypothesis, a concept born from the planet's strange balance of pressure, temperature, and composition. If true, it could mean that this distant world, 124 light-years away, holds vast seas of liquid water sealed beneath thick clouds of hydrogen and vapor, a global ocean untouched by sun or sky. For decades, the presence of oceans has been the quiet dream of exoplanet science. On Earth, water is the matrix of life, the stage upon which chemistry becomes biology. Every drop is a laboratory of molecular exchange. Finding oceans beyond Earth, then, isn't merely about locating water. It's about finding the conditions that allow complexity to bloom. But K2-18b complicates that dream. It is much larger than Earth, with a gravity so strong that its atmosphere might stretch thousands of kilometers deep. The hydrogen envelope that surrounds it would create immense pressure at the ocean's surface, turning the boundary between air and sea into a place of crushing density and alien chemistry. Under such conditions, liquid water could exist not as the gentle blue we know, but as a superheated, high-pressure medium, dense, murky, and strange. If life exists there, it would need to thrive in darkness, perhaps feeding on chemical energy rather than light. On Earth, similar ecosystems exist around hydrothermal vents deep in our oceans, where sunlight never reaches. There, bacteria transform chemical gradients into food, building entire communities in the shadows. If nature can do it here, why not there? The same physics applies. Hydrogen, water, carbon, and energy. The recipe doesn't change, only the setting. Models suggest that below K2-18b's clouds, a transition zone might separate gaseous hydrogen from liquid water. In that region, molecules like methane, ammonia, and dimethyl sulfide could form naturally or be altered by living processes. JWST's readings hint at such chemistry. The challenge lies in proving it. We can't yet see the ocean directly. We can only infer its presence through spectral clues, ratios of gases that suggest evaporation, circulation, and condensation. Like listening to waves from behind a wall, we sense motion without sight. If confirmed, the hidden ocean hypothesis would rewrite our understanding of habitability. Until now, scientists believed that only Earth-like planets, rocky worlds with thin atmospheres, could host liquid water. K2-18b defies that rule, showing that even sub-Neptune-sized planets long thought too hostile, might cradle oceans beneath their veils. This expands the habitable zone of the universe exponentially. Every mini Neptune out there could conceal a secret ocean, each one a possible cradle of life. What Webb has given us is not proof, but possibility, a shimmering doorway into an unseen sea. Whether K2-18b's waters teem with chemistry or slumber in sterile quiet, they remind us that life's potential hides in the unlikeliest places. Sometimes it is the worlds we can't fully see that hold the greatest truths. And so, we stand at the edge of discovery, a point where science begins to blur into wonder. The James Webb Space Telescope has not yet given us absolute proof of life beyond Earth, but it has given us something just as powerful: hope. Every spectrum it captures, every faint chemical trace in the light of distant stars, brings us one step closer to answering the oldest question we've ever asked. Are we alone? K2-18b, with its veiled atmosphere and the mystery of its hidden ocean, may hold the first whispers of an answer. Perhaps it's a silent, lifeless sea, or perhaps, beneath that hydrogen sky, something stirs, something that breathes, evolves, and dreams in the darkness. For now, all we have are signals, but signals are where all stories begin. This is not the end. It's the beginning of a much larger journey. In part 2, we'll dive deeper into the possibilities. How alien oceans could sustain life without sunlight. What biosignatures truly mean in the grand puzzle of astrobiology, and whether we're finally close to detecting the unmistakable fingerprint of life itself. Until then, let the stars remind you, the answers we seek are already shining. We just have to learn how to see them.